Okay, so we can make the area a function of the circumference, all right, by solving our circumference formula for R. Okay, and the reason why we're doing this is because, again, we have information about the circumference. We don't have information about R. Okay, let's clean this up a little bit. So this is going to become c squared 4 pi squared. And then we can cancel some things. We can cancel a 4 pi, and we're left with c squared over pi. So now we have our surface area as a function of c squared. Excuse me, of a function of the circumference. All right. So now we have to find the error in surface error. Okay, so the error of the surface area would be if we apply the error of the circumference, what would the difference in area be? That's exactly what delta A is, right, on the curve. But what we're going to do, remember sometimes on the function is hard to calculate, we can approximate it on the tangent line. So this is going to be approximated by the differential of A. So this is our strategy. So the maximum error is really this delta A, the change in the area, the change in the surface area given the error of the circumference. And we're going to approximate it using the differential, which is calculated, it's the difference on the slope. Excuse me, the difference on the tangent. Okay, so remember that the error of the circumference, we can notate that as delta C. Whoops, but it's not approximately. And delta C is exactly the differential of C. Okay, and so here's what we have. We know that delta A is approximated by the differential, and the differential is equal to A prime dc. Okay, so that's what we're working with. So if we look at A prime, here I'll switch colors to break it up all that green. Here's our A. The variable is the circumference, because that's what could have the error. The pi is a constant. So when we take the derivative, we're really just taking the derivative of c squared, which is 2c. And then it's still over pi. So 2c over pi. So there you go. All right, so that's what we're looking at for the differential. And now we have that dc was given to us in the very first part of the problem as 0.05. Right, and then the circumference is 84. So we can put all that stuff in. So C is given in the problem as 84 centimeters, and DC, or the delta C, is 0.05. Okay, so that takes care of the C, and that takes care of delta C. So now we have this. So it's going to be 2 times 0.05 over pi. Oh, goodness gracious. That's not right. 84 times 0.05. Okay, and if we clean this up, we should get something like this. 27 centimeters squared. All right, and actually let me just check. I think I got this delta C incorrect, guys. I'm sorry. I think the textbook says that it's 0.5, and I wrote 0.05. Oh, goodness. Okay, so hopefully we caught that mistake. Sorry about that. All right, so it changes a couple things. Oh my gosh. Hopefully you guys are still on board. Okay, so it's 0.5. So it simplifies to 84 over pi. That's why I caught my mistake, is because it should simplify to 84 over pi. And then that is approximately 27 centimeters squared. Oh boy. Okay, so like I said, hopefully I didn't lose you guys and you guys could follow me despite my error. All right, so that's the first part. And now we're going to talk about the relative error. And the relative error is really, it's behaving as a percentage compared to the whole surface area. So if dA is the error in surface area, right, if we mess up the circumference by 0.5 centimeters, how does that relate to the total surface area? All right, so we see it's a fraction, so it's going to be some sort of percentage. So we just calculate dA to be 84 over pi. The surface area, we have our equation, c squared over pi, so 84 squared over pi. Okay, lots of things cancel, and we're left with 1 over 84, which is about 0.012, or 1.2%. So if the surface area, or excuse me, the circumference is off by 0.5 centimeters squared, the relative error in surface area is 1.2%. All right, so we're going to do the whole thing over again, this time with volume. All right, and if you guys are feeling confident enough, go ahead and push pause and see if you can do the volume by yourself. And then let me just, sorry, let me erase this. Let me give you the formula for the volume of a sphere in case we forgot for whatever reason. So we're going to repeat for the volume of this sphere if the circumference has a 0.5 centimeter square or centimeter error. And the volume is 4/3 pi r cubed. Okay, and remember the circumference is 84 centimeters, and then the error is 0.5 centimeters, not 0.05 centimeters. Okay, so again, go ahead and push pause and see how you do. All right, so hopefully the first thing you guys did, since we have circumference and our formulas in terms of radius, you remembered that circumference is 2 pi r. So r is c over 2 pi. And you made that substitution for r. Okay, and we clean it up. So c cubed over 8 pi cubed. All right, lots of things cancel. Okay, so it's going to simplify to c cubed is left on top. All right, sorry for the interruption. So anywho, we have this function of the volume in terms of the circumference, okay? And remember, we want to calculate the error in volume given that there's an error in circumference, and we're going to approximate it with the differentials. So we're going to approximate it using dV, and again, dV is equal to V prime dc. All right, and then in V prime, remember the only variable is the c, so we're going to change, when we take the derivative, that will turn into 3c squared over 6 pi squared dc. And we'll clean that up. 3 over 6 simplifies to 1 over 2. Okay. All right, and then we know that C is 84. And DC is 0.5. Okay, so clean that up a little bit. And this simplifies to 1,764 divided by pi squared. And then that's approximately this. And the meters, excuse me, the units, because it's volume, units are going to be cubed. All right, so that's the maximum error in volume, approximated using the differentials. And now we're going to do the same thing we did before for the relative error. And again, it's relative to the overall volume. Okay, so if we have, this looks like a large area or a large error, right? 178 centimeters cubed. But is it big relative to the overall volume? So that's why the relative error is so important. So it may look big to us, but if we have a ginormous sphere, it might not be that big. All right, and then the volume is, we calculated before, it's C cubed over 6 pi squared. Okay, we clean that up. And it ends up being 1 over 56, which is approximately 0.018. So 1.8%. So even though the error looks big to us, it's relatively small compared to the overall volume of this sphere.